To continue on with our study of Chapter 7, I'm going to today talk about strategies for strengthening materials and making them more resistant to slip and dislocation motion. So as we discussed in the last lecture, grain boundaries can act as barriers to slip because of the different directions that material wants to slip along at the grain boundary due to the orientation of the crystal. So since grain boundaries are the barriers to slip, you can increase the strength by increasing the angle of misorientation or by making smaller grains, which are more barriers to slip. So if you have more grains within the material, then your grains are smaller and you've got more grain boundaries, and so a material won't slip as much. This is the Hall-Petch method for strengthening a material, and it's governed by the Hall-Petch equation, which is an empirical equation. And the empirical equation gives the yield strength of the material sigma sub y, and it's equal to the value at the intercept, or the null value for the material before you reduce the grain size, sigma naught, plus ky, which is a constant that comes from the fit, times the diameter of the average grain size to the -1/2 power. Okay, so that shows you that as the grains are smaller, the yield strength goes up. Okay, as an example problem here, briefly explain why hexagonal close pack metals are typically more brittle than FCC and BCC metals based upon Table 7.1, which tells us about slip systems for face-centered cubic, body-centered cubic, and hexagonal close pack metals. Okay, so if you look at this, for the FCC metals like copper, aluminum, and so on and so forth. Remember, their slip plane is the 1-1-1 direction, or 1-1-1 plane, family of planes, and the slip direction is the 1-1 bar 0 direction. That has 12 slip systems associated with it. For body-centered cubic metals like iron, tungsten, potassium, so on and so forth, they have at least 12, and for some of them more, 24 slip systems. So that's a lot of slip systems for these different families of planes. Now, if you look for the hexagonal close pack metals like cadmium, magnesium, titanium, things like that, you can see that for each slip plane, there's only a few slip systems. So they have 3, 3, and 6. So that's a lot less than the number of slip directions and slip systems for the FCC and BCC metals. So because there's fewer slip systems, then of course less slippage occurs. If less slippage occurs, then instead of plastic deformation, stretching it out, it's just going to break. So that makes HCP metals more brittle than the FCC and the BCC metals. Okay, 4 strategies for strengthening. Number 2, form solid solutions. So number 1 was to reduce the grain size. Basically anything, though, anything that causes less slippage is going to strengthen the material. And if you can form a solid solution or an alloy, that's another way to do it. And the reason is that the impurity atoms actually distort the lattice and they generate lattice strains. They generate strains in the lattice. And remember that like strains repel one another. So if you had 2 dislocations moving towards one another, unlike strains like a compression and a tension attracted one another, but compressions repelled other compressions. So if you have a substitutional atom in there, a substitutional impurity, that generates a lattice strain, and then what that does is it prevents like strains from moving towards it, so it forms sort of a barrier. And these can happen with either smaller substitutional impurities, which cause tension, or larger substitutional impurities, okay? So either one can help. So small impurities, they have a tendency to concentrate at the dislocation. So this is another reason that solid solution alloying works out. What'll happen is if there's an edge dislocation or something in the material, the impurity atoms will walk around, kind of hop around randomly until they reach one of these dislocations. When they hit the dislocation, they actually cause it to relieve some of the lattice stress. And because it relieves some of the stress, that lowers the energy for the system, and so they're less likely to hop out of that position. So they stay there. it cancels the dislocation and compressive strain, but because it would increase the energy for that little guy to hop back out, it doesn't do it. It stays there, and that acts as a barrier to that dislocation moving and slipping around. You can also get larger impurities to help you out. They also have the tendency to concentrate at dislocations, but in that case they have a tendency to concentrate on the other side of the edge dislocation, and they relieve the stress of the tension on that side because they're big and they sit in there and they fill that hole, okay? And then yet again, they've lowered the energy of the system when they move to that spot, and so they don't want to hop out, and so they stay and the dislocation can't move. Here's an example of solid solution strengthening, say that 10 times fast, in copper, okay? So nickel would be the alloy that it's forming here. So this is a plot showing the weight percent increase of nickel, and then as the weight percent increase of nickel goes across here, you can see an increase in both the tensile strength and the yield strength of the material. It's a very significant increase. It starts off at, say, 230-ish megapascals, and it goes up to above 400 by the time you get to a weight percent of, say, 50 or so. And then the yield strength, same way. It starts out here at maybe 80 or so megapascals, and it goes up to over 150 by the time you increase the weight percentage of nickel. So that shows you, how big an effect that solid solution, forming a solid solution, can have on increasing the strength of the material because it prevents the slip. There's an empirical relation relating those two. Yet again, it's just a fit to the curve. There's no fundamental real thing here. It just shows that the yield strength goes as the concentration of the 1/2 power roughly. And alloying is going to increase yield strength and tensile strength. Okay, now in terms of the next one of the 4 strategies for strengthening, there's precipitation strengthening. This is covered in a lot more depth in Chapter 11, but basically, to sum up, the strength and the hardness of some metal alloys is enhanced by the formation of extremely small but uniformly dispersed particles of another phase or a precipitate of that phase within the original matrix. And this has to be accomplished by phase transformations that are induced by heat treatment. So basically you heat treat it. And this process, the whole process, is called precipitation hardening because the small particles of the new phase are termed the precipitates. And then of course they can act as boundaries to slip for much the same reason that a grain boundary or a solid solution alloy can act as a boundary to slip. It's harder for that dislocation to move through the precipitate because it's kind of like having a different grain of material in there, and it's hard to slip along that thing. Okay? And you can see that the yield strength is going to go as 1 over the concentration of that. Okay, this is a really common method for aluminum in particular. Aluminum gets used in a lot of aircraft, so being able to make aluminum a lot stronger makes a whole bunch of people that are flying in these planes much, much safer. And those alloys commonly employ precipitation hardening. So what you see down here at the bottom is a transmission electron microscope image of an aluminum alloy. The light matrix is the aluminum solid solution, and then the dark particles are the precipitates. And what they are is denser and more copper-rich regions than the matrix. Okay, the next method for strengthening material is to do cold work. It's also called strain hardening. And basically what this is the deformation at room temperature for most materials. But anyway, cold is a relative term. It's cold relative to the melting point of the material, okay? So cold work, much less than the melting point of the material operations. And there's a lot of operations that people commonly employ in factories to get this to happen. So one of them is rolling it out. That's a really common way. So you have a sheet of metal and you pass it between 2 rollers that you usually cool with water or some other form because it's going to heat up as you mush it. And then that makes the cross-sectional area of of the metal plate much smaller. You can also get it through forging, where you take a piece of metal, you put it into a die, and then you just push real hard on it to get it to take that shape. Again, you're applying a lot of force to it. You can get it through drawing, where you have some sort of die, but it's not closed off on either side, and you push it through, maybe to make a cylinder into a triangular shape or whatever, and it goes through, reducing the cross-sectional area. And then finally, there's extrusion, where you use a ram and you force it through the die on the other side. Okay, so this causes a change in the cross-sectional area of the material. It causes it to reduce, and so what you do is you calculate the percent of cold work by calculating the percent change in the area. So A naught would be the initial area, cross-sectional area of your material, and then AD is the cross-sectional area after it's been through cold work. And you take that difference over the initial and multiply times 100% to get your percent cold work of the material. So here you can see what's going on and how cold work influences material and material properties and why it makes it stronger. This is a scanning electron microscope image, and of course the dislocations and the slips, the defects, show up as these little dark lines within the material. So these are the defect regions. And you can see that this is for titanium after it's been cold worked, and you can see that the dislocations are all tangled up. It looks kind of like spaghetti there. So since the dislocations are entangled with one another, and there's more dislocations that have been formed after the cold work, the reason that this helps is because the dislocations, remember, for like strains, they have a tendency to repel one another. And so if you get them in there and you get them all tangled up, dislocation motion actually becomes more difficult as time goes on, and that's why cold work really makes the material much more stronger. Dislocation density is actually usually measured by measuring the total length in the previous image of all those little squiggly lines. If you sum up the length of all those lines end to end, and then you divide it by the volume of the material that you've looked at, then that gives you your dislocation density. Now, typically, all materials have some defects. So even if you're very super careful and you haven't put it through any cold work or done anything to it, and you're growing a single crystal of material, then you're still going to get a dislocation density of 10 to the 3 millimeters to the -2 power. But as you increase it, as you deform it, put it through cold work or something like that, then you can get it to grow by 6 or 7 orders of magnitude to 10 to the 10th inverse millimeters squared. And then if you want to recover that material and make it nice again, reduce the number of dislocations, you can put it through a heat treatment, and that's going to reduce the density back down a couple orders of magnitude, 3, 4 orders of magnitude, 10 to the 5th, 10 to the 6th inverse millimeters squared. Okay? Now remember, your yield stress is going to increase as your dislocation density increases. As you have more defects, more dislocations, you're going to have a stronger material. So that shows up here in this material. It shows the impact of cold work. As the cold work is increased, so this is the percent cold work indicated here by the different colors of the line. So you have 0% cold work for this low carbon steel in the green, 4% in the blue, and 24% here in the red. And you can see that the stress that it can withstand has gone way up as you increase the cold work. The tensile strength also increases, but what's going to happen is the ductility decreases. You can see the truncation of these curves. This is the 0% cold work. It underwent a whole lot more strain before failure than the 4% cold work or the 24% cold work, which could undergo the least amount of strain. Okay? Okay, so mechanical property alterations due to cold working. So if you look, for example, at what happens when you cold work copper, let's say that you pulled it out, applied some kind of stress, put it through a die or whatever, so that the initial diameter of the thing was 15.2 millimeters, and then it goes to 12.2 millimeters. So then you can calculate the percent cold work, it's going to be proportional to the radius of the diameter squared differences. So 15.2 squared minus 12.2 squared over 12.2 squared will give you a percentage of cold work of 35.6% cold work. So this material has gone through 35.6% cold work. Now if you look at this plot for copper and shows you the impact on the yield strength, tensile strength, and ductility for various percent cold works. If you take that cold work that we calculated in the previous slide and then you read off on the graph what's happening, it can increase the yield strength from something like 150 to 300 megapascals. It can increase the tensile strength from something like, oh gosh, 250 or so to 340 megapascals, and it can drop that ductility from over 40% down to 7% of ductility. So anytime basically you increase the strength of your material, you're going to sacrifice the ductility of the material. And that just makes sense. Okay, so here's another example for you. Experimentally, it's been observed for single crystals of a number of metals that the critically resolved shear stress is a function of the dislocation density. So here, the critically resolved shear stress is equal to a constant tau naught plus another constant A times the root of the dislocation density. So for copper, the critically resolved shear stress is 2.1 megapascals at a dislocation density of 10 to the 5th inverse millimeter squared. If it's known that the value for A is 0.00635 megapascals times millimeters, compute the critically resolved shear stress at a dislocation density of 10 to the 7th inverse millimeter squared. So this is a pretty simple plug and chug. You just take that equation that's given, plug in values for it. So your critically resolved shear stress is 2.1 megapascals. You don't know tau naught, you've got to solve for that, but then it's plus 0.00635 times the root of 10 to the 5th. Doing a little simple manipulation, you solve for tau naught and you get 0.1 megapascals. And now you can plug that back into your equation for the new dislocation density of 10 to the 7th inverse millimeter squared, and you get your critically resolved shear stress as 0.1 plus 0.00635 times the square root of 10 to the 7th is 20.1 megapascals, okay? So you can see that for just a small, well, not a small, a factor of 100 difference in the dislocation density can result in also about a factor of 100, factor of 10 difference in the critically resolved shear stress. Okay, now after you've cold worked it, if for some reason you would like to get rid of some of the effects, decrease the number of dislocations, maybe because you want to recover some of that ductility, for example, then you can put it through a heat treatment. This is called annealing the material. So you put it through, for example, a 1-hour heat treatment at some annealing temperature, and then what that'll do is it'll, again, decrease the tensile strength, but it'll increase your ductility, all right? So this helps nullify some or all, if you do it for enough or for hot enough or long enough. It affects some or all of the effects of cold work, okay? So there's 3 annealing stages. So you start putting it through this heat treatment, and the first thing that happens is recovery, and then it recrystallizes, and then the grains begin to grow again, okay? So that's what happens as the time and temperature change. Okay, so during recovery, what happens is there's a couple of things. It causes those dislocations to move more easily when it's hotter, and when the dislocations move, they have a tendency to annihilate one another. So you get a region of compressive stress moving to a region of tension, and they annihilate. So that happens. Another thing is that if there's some obstacle like precipitate or something, solid solution, it prevents the dislocation from moving even with the heat, then maybe it can move the other way to a boundary or the surface, and then it can move up and move out. You remember what we talked about with heating and the expansion and the vacancies hopping, and they can hop up towards the surface until it just forms a little step and it goes away. We saw a movie of that earlier in the semester. So that's another thing that can happen during recovery. So basically, during recovery, your dislocations move around until they annihilate or go away. Another thing that then happens during the heat treatment is that it can recrystallize. So what that means is that it forms new grains that have those low dislocation densities. They're smaller in size, and then the grains grow and consume and replace the parent cold work grains. Now, these crystals are going to nucleate preferentially at sites that have high strains in the lattice. That's what kind of gives it the kick that it needs to form and nucleate that new grain. So they're gonna initiate at points of high stress within your material. And then the cold work grains you can see here over time. This was our original material. You can see these cold work grains, and you can see some of these little new crystals starting to nucleate in there just after, you know, a few seconds, 3 seconds. And then as time goes on, at 4 seconds, you can see more and more of those little crystals forming, and then after 8 seconds it looks like all the old grains are just gone. Okay, now this recrystallization temperature that you want to hold it at is not at the melting temperature, so it's important to understand that you're not melting the material. That's starting all over from scratch. What you're doing instead is you're taking it to 1/3 to the half of the melting temperature and holding it there below the melting point and letting new grains form. Now, after you have those new grains form, you hold it at that temperature and let some time pass, and then the average grain size is going to increase. You're going to see the smaller grains shrink and ultimately disappear as they're consumed by those larger grains, because the grain boundaries have energy, and the energy is reduced with fewer large grains as opposed to a lot of smaller grains. Okay, and so this shows the process. You had, after 8 seconds, all those little tiny grains forming, but then if you let it go for a little while, after 15 minutes, you can see that you've got a lot larger grains than you did at the 8-second time. This is described by this empirical relation right here, d to the n minus d naught to the n equals kt. Here, T is the elapsed time, K is a coefficient that depends upon what kind of material you got and the temperature that you're holding it at. D is the grain diameter at the time after you've let it elapse. N is an exponent that's typically about 2, and D naught is the initial grain size once the recrystallization has happened. Okay, for this example problem, it says, you know, using this graph, use the information in the graph to compute the length of time required for the average grain diameter to increase from 0.01 to 0.1 millimeters at 500 degrees C for this brass material, and then use that to find K if you assume that the exponent N is equal to 2. Okay, so first of all, I want to draw your attention to the fact that there's different lines on this plot for different temperatures. Okay, remember your annealing temperature can be any temperature as long as it's, you know, 1/3 to 1/2 of your melting temperature. So see here, we have a range of temperatures from 500 to 850 degrees C. Okay, now you can notice that the higher temperatures are going to cause more rapid grain growth. Here, this is a plot of the grain diameter in millimeters versus time, and you can see that it reaches those larger grain sizes much faster for those higher temperatures. Okay, but what we're interested in is what happens at 500 degrees C, which is this lowest plot right here, and it's asking for the time required, the length of time required for the grain diameter to go from 0.01 to 0.1. Okay, so if we look at this plot, the 0.01 grain size is down here on this bottom line. And so you can see that if you read off how much, where it is in that period of time, it looks like it's at about 5 minutes or so. Okay, now it goes from 0.01 to 0.1. 0.1 is the next line up here, and if you look at the intersection of our 500 degrees C curve with the 0.1 point on the graph, then it looks like that happens at about say 5,000 minutes or so. So we've got an elapsed time of about 5,000 minutes from our beginning here, from 0.01 to at 0.1. Okay, so that's the time interval that I'm going to use. That's the time interval. And now I'm going to use that time interval to find my constant K, assuming N equals to 2. I do that on the next slide here. I'm going to plug into that equation the time that I'm interested in after about 5,000 minutes, the grain size is 0.1 millimeters, and then I'm going to square that. And then I subtract off the initial grain size, which is about 0.01 millimeters, and I'm going to square that, and then that's equal to KT. T is 5,000 minutes or so, and then I'm solving for K. And if I do that, then I get K is 2 times 10 to the minus 6 millimeters squared per minute. Okay, what's shown here is what are the impacts on the annealing temperature of the tensile strength and on the ductility for a particular material. I believe here it's brass. And then what's happened is the brass has been annealed at these various temperatures for an hour. So this is all showing what happens after an hour. Okay, so it's annealed. You can see that for the lower temperatures, for lower annealing temperatures, there's not tons of impact on that tensile strength. It's still very high, okay? But then you can see that the tensile strength starts to drop pretty significantly once you reach about 300 degrees C, and then it kind of plateaus out in how well it does here as you reach some of those higher temperatures. So it looks like, you know, you get a big increase in effect between, say, about 200 degrees Celsius and, say, 500 degrees Celsius, but once you've reached the 500 degrees Celsius point, there's really no point in turning it up much more because you don't see many returns for that. And then, of course, the ductility goes as sort of the inverse of the tensile strength. That always seems to be the way. The stronger the material is, the more brittle it is, and the less ductile. All right, now another thing is this bottom plot shows the grain size, the average grain size after an hour of annealing at these temperatures, and you can see that it kind of plateaus out here at about 400 degrees C. You're still seeing pretty small grains, but then it goes up very rapidly as you go up in temperature, and so you can see that you're getting grains of about 0.04 millimeters in diameter once you're at the 650 to 700 degrees Celsius. And that kind of makes sense, right? If you have a larger grain, your tensile strength is going to be lower because there's fewer grain boundaries, and then of course the grain boundaries act as a barrier to slippage. Now that recrystallization temperature was a line shown on the previous plot. The recrystallization temperature is defined as the minimum temperature at which recrystallization just reaches completion in an hour. And it's usually between 30 and 60% of the melting point of the material. So for a specific metal or alloy, your recrystallization temperature is going to depend a little bit on the percent of cold work. And the reason for that is because there's, of course, the nucleation sites are at points of high strain in the material, and the points of high strain are where the dislocations are. So if you've done more cold work, you're going to have more dislocations and therefore more nucleations. And if you haven't done a lot of cold work, your dislocation density is going to be very low, and so new grains aren't going to nucleate there, okay? So what you're going to see is that your recrystallization temperature is going to decrease with increasing cold work because you've got more nucleation sites if you've done more cold work. The purity of the metal, your recrystallization temperature is also going to decrease with increasing purity, and that's another relationship that you typically see. Okay, well, I hope that was interesting and useful, and as always, if you have any questions, I'll see you in class.